Hello and welcome to another episode of Risky Business. Before we begin today, I want to point out that I have a poll here on Twitter. I pinned it so it's easy to find. It's got 5 days left on it, and it's whether I should hire an artist to make better thumbnails for the YouTube videos. And right now, it seems like most people like the thumbnails that we already have. But if you would like better thumbnails, be sure to go here and vote yes, because I'll be going with whatever the poll says. So if people don't want new thumbnails, then we're not going to get new thumbnails. And I'll point out what we're talking about here for people who don't use the YouTube archive. So I have thumbnails for all my videos, and right now I make these myself, as you can probably tell by the poor quality. And for the High-Five 1 videos, I just took an image from the crowdsource page that they have, and I cropped it and scaled it to be suitable as a thumbnail. And so all of these have all of the High-Five 1 content has the same thumbnail. So you can't really visually distinguish episodes. You have to look at the title of the video to see which is which is one thing that we would improve if we had an artist doing proper thumbnails for us. And also technically, like, I'm not in the right to be using this image. So if SiFive didn't want me to at any point, they could make me change this too. So that's one thing to point out. But we are going to stick with these thumbnails unless told otherwise, or if people decide they want better thumbnails, in which case I'd hire an artist to do that. So be sure to vote on that if you care about that at all. And now let's get into the actual content for today. So we left off yesterday, or not yesterday, but last time we streamed, we took a look at the PLIC init and PLIC set threshold. So we understand everything that this code is doing. This PLIC init. One thing that's interesting is it sets the threshold to 0, which kind of goes against the disable all interrupts, because you can use thresholding to block interrupts as well. But I guess they're just zeroing it out in the init. And as far as disabling interrupts go, they're just talking about zeroing out the enable memory. And then the set threshold here is really straightforward too. It basically works the same way that these things work that we discovered in the PLIC init. And then now we're moving on to this PLIC enable interrupt, which is what we're going to be looking at today. And so we want to take a look at this a little bit closer than the other ones because it's a little bit different. So first of all, we get the hardware thread ID using read CSR. We know about that. And then we get this pointer, and that is computed by the base address of the PLIC plus the enable offset, and then the hardware thread shifted by enable shift per target, and then we're adding source shifted right 3 places. So so this looks familiar. The base address, the enable offset, and the enable shift per target, I believe that's the same thing we were doing here. Yeah, that's the same thing. So we know what this much is doing, right? That's putting us, let me find the document here. Is it this one? Yeah. So here's the enables. And so it's computing, if it was hardware thread 0, it would go to 0x0C0020000. And then if it was hardware thread ID 1, it would go to this 2080 address, and so on and so forth. So that's what that's computing. But then we also want to know about this source shifted right 3 places. So we know that the target enables, there's 0x80 between them, which is I believe 128 bits or 16 bytes. And every bit in that represents a source. And we have 52, if I'm remembering correctly, we have 52 different sources that this HiFive1 actually supports, which is the first 5 or 7, the first 7 bytes. So we're doing source shifted right 3, so we're finding a specific source is obviously what this is doing. But we want to understand that. So there is a PLIC source that we're passing in, which I think is just an integer. Let's double check that. So PLIC source. That's probably in PLIC driver.h. Yeah, so that's just unsigned integer. And we're taking that value shifted right by 3. So I'd like to see a use case of this enable interrupt, if we're using it at all. So let's go to the demo program here. Okay, so here's some examples of enable interrupt being called. So there's like int device button 0, int device button 1, button 2. So first of all, let's go back to the documentation. And one of these documents has the list of 52 that we actually support. So let's see, which one was that? Was it the platform memory map? I think it might have been for the specific chip that we have. Yeah, okay, so it's this document here. And so you can see there's these 52 interrupts, and each one has a number and it says what the source is. And here's something interesting. The PLIC on FE310-G000 has a 3-bit programmable interrupt priority field. Oh, that would be the priority field though. That's not what we care about. I was thinking maybe that's had something to do with the shifting 3 to the right, but maybe not. But int device button 0, button 1, button 2, those are some example interrupts that we apparently have defined. And I guess I don't see an obvious mapping onto the sources, what those would correspond to. Probably GPIO, since this is a demo GPIO thing. That would just be a wild guess that it would be mapped to the GPIO stuff. So let's take a look now at where these interrupts where they're defined. So we are looking for let's see here, interrupt. Let's see, int device is what we're looking for. So that must be defined in the platform or something. So let's check the encoding first of all. It's not there. And let's check the platform.h, and it's not in that. So it doesn't look like it's in any of the source files I currently have open. So we might need to do a little bit of hunting again. So one thing to note is these are wrapped in an ifdef has board buttons. So that could be something to search for as well. I think I'm going to search this with egg, and that pulled up environments SiFive1.h. So it looks like they're defined in this file here. So these are defined as int GPIO base plus an offset. So we want to find int GPIO base as well. Which apparently is not defined in this file. So we might need to do some hunting again. Okay, that's defined in the platform.h, and it's defined to be 8. So int device button 0 is 8 plus the button 0 offset, for example. So let's go back to the SiFive1 now. And take a look at those offsets. So the offset is 15, 30, and 31 for those buttons. So it also says these are specific to the Freedom E300 RD dev kit. So those are probably not actually relevant to us because we're using the SiFive1, not the RD dev kit. So I think this code here actually doesn't get run, or doesn't get compiled, I mean, because I believe we do not have those buttons. So in that case, that might be not so relevant to us. It looks like that's the only place we're enabling interrupts though in this demo program. So even though it's not necessarily relevant to us, I do want to take a look at it because it's an example of the use case of the PLIC enable interrupt, which is something we want to understand. So let me see here. If we have interrupt numbers 0 to 52, and each one corresponds to a bit, then we're computing that number. We're finding the proper bit when we're doing the enable interrupt. So if we go back to the PLIC driver.c, so you can see it's doing current r equals 1 shifted source and 0x7, and then it's setting that in the current pointer. And the current pointer is pointing to this memory here. Or no, this memory here. Or whichever target is the one we're on. And then it's doing source shifted right 3 places. So I'm not sure I'm not sure I'm following that part of it yet. So we have like int device button 0 would be 8 plus 15. And then we're shifting that value 3 places to the right. So first of all, let's open up Milton here. So like we know that 8 in binary is 1000, and so that's the base address. And then we're saying that plus 15. So 15 I believe in hex that's an F. So that would be like 1111, wouldn't it? So if I go to Google here and do a little bit of math. I want to say like 8 plus 15 to hex. So that says 0x17. Let me just confirm that that's not counting the 8 and the 15 as hex. So 23 to hex should be 0x17. So yeah, we're getting the value 0x17. So I wonder if we can say 0x17 to binary. So this is the value in binary, 10111. So we're taking this address and we're adding 0x17 to it. So would 17 be the interrupt number then? Which would be in the GPIO section between 0 and 31. Is there like a mapping of the GPIO? I want to know more about the GPIO pins. Because I'm pretty sure what we're doing here is we're mapping into the part of the enable bits that's doing GPIO. Let's take a look at that memory map again, or the interrupts, I mean. So, okay, well, we know that interrupt number 8 is GPIO 0. And in our code, the GPIO base was set to 8. So that would be correct then. So 17 is one of the GPIOs. And so I don't know where it would be defined that that particular GPIO corresponds to a button, but it probably wouldn't be defined in the FE310-G000, would it? Because that's something that's specific to the board as far as I understand. Like the RD dev kit is the thing that has those buttons. So I think that would be the thing that defines the mapping there. So I'm not sure if any of these documents are even gonna specify that. That's the thing that's got me wondering here. But for now, I think it would be safe for us to not worry about it, because it seems like we understand what the code is doing. It's just that we don't have the documentation that's specifying that that bit corresponds to a specific button. And we don't really care about that. So I think it's safe to say that we know that that what this code is doing is it's jumping to here, and then it's moving forward 0x17 because moving forward 0x8 gets you to the GPIO 0 bit, and then the additional 15 0x15 that we're moving gets you to a specific GPIO that happens to correspond to a button. So I'm willing to accept that. I feel like that is something that I understand. And now we take that pointer, and then we're saying r equals, and r equals is how you set a bit. So we're setting that bit on is what we're doing here. And to set it on, the mask we're doing is the source and 0x7, and then 1 shifted that amount. So I wonder, can Google do and? We're really pushing Google to the limit here with what it can calculate. So we want to do 0x17 and 0x7. I think we might have to move over to Wolfram Alpha to do this. So if I say 0x17 and 0x7, I suppose we could do this by hand too. So it doesn't look like that interpreted the way I was hoping it would. Let's do it by hand. So if we have 0x17, so let's think about what that would be. So if we say 1, 2, 4, 8, so 16, 17, so it would be 1, 0, 0, 0, 1, and then 7 would be this, so that would be 0, 0, 1, 1, 1. And then we're doing an and so that would be 1, 0, 0, 0, 0. If I'm doing my math correctly. So yeah, 0x17 and 0x7, and we're saying 1 shifted left that many places. So in this code, that would be 1 shifted 1 place. So if I say How do you draw an ampersand? So if we say here's my terrible little ampersand, and then this is a shift by 1, we get that value there. And then we're setting that bit. So that doesn't really make sense to me that we'd be setting that particular bit. So if I'm saying I have 0x17 and then I'm shifting it right 3, so let's do that math by hand as well. So if I have 17, and then I'm going to do shift by 3. So that would be the 0 goes off the end. So this shifts 1, 2, 3. Okay, and now you can see these do match. It's 1/28. One shifted left, 0x17 and 0x7. How does that give 1/28? I must be doing something wrong with my math then. Because if what I've drawn here was right, it would give you 2. So now I'm even more confused. Well, I mean, 1/28. 1/28 is 0x80, which is an interesting value for sure. considering that we're moving in strides of 0x80. So if we say current r equals 0x80, that doesn't really make sense to me. So I kind of want to write a little test program like Miblo has done to confirm that, because that doesn't make sense to me. The math that I did by hand here is not giving 128, it's giving 2, which is a very different number, to say the least. But they match, which would suggest that it's right, but clearly not if it's 128. I mean, and is the one where they both have to be, both bits have to be 1 in order for it to give a 1, right? So, and I'm pretty sure that these values here are 17 and 7. So I can count off the 1 on the bottom for you, right? 1, 2, 3, 4, 5, 6, 7. So that one's definitely right. And then just thinking about 17, right? We know this would be 16, so that has to be 17. So it seems like that would be right. Or wait a minute. It's hex though. That's where I'm wrong, Miblo. I'm doing 17 in decimal. Right. This is 17 decimal, but it's 0x17 hex. Yeah. It looks like we just figured it out at the same time, Miblo. I was thinking decimal when it's actually hexadecimal. So if I say 0x17 to binary, so this is the correct value for 0x17, 10111. So let's do this again. So if we have 10111, and then we have 7, which should be the same as in decimal. So 7 hexadecimal, I believe, would still be like this. And then when we AND them, we get 00111. And then we are, what are we doing? We're shifting left by 1, right? So if we do a shift by 1, we get 0, 1, 1, 1, 0. And then if we say 0, 1, 1, 1, 0 in hex, or in decimal, that gave me 14. So what am I doing wrong now? So it was 10111, right? Yeah, 10111. And then we're saying and 0x7. So I'll do 0x7 to binary, but I'm pretty sure it's 111. Yeah. Oh yeah, that's the thing. I did it backwards, Miblo. You're right. So this part is wrong. The thing that we're doing is 0, 0, 0, 1 shifted, or that many places. So we're saying we're shifting it 7 places. So 1, 2, 3, 4, 5, 6, 7. So it becomes 1, 0, 0, 0, 0, 0, 0, 0. And that should be the 128. So if I say 0b 1 0 0 0 0 0 0 0 to decimal, that's 128. Okay, so we have made it through the confusion, and we have the correct value now. So that much makes sense. Now we need to confirm it on the other side too. So when we're doing this this computation for the address of the pointer, we're doing source shifted right 3. So source is 0x17 in this example. And so that's the 10111. And we're shifting it right 3 places. And so if I do 10111, and then I shift it right 3 places, these all fall off the end. And this one ends up right here. So 10010, or this would be a 0. So now those don't match. The right shift in C, that doesn't wrap, does it? Like the ones that are going off the end just get lost, right? So it seems like that would be adding 2. So if we're adding 2 to this, but then we're saying current equals current or equals the 128. Yeah, Miblo, that would be this line right here. Source right shift 3, which we're adding that to this address here. So that's the part that I'm confused the most about. Like, conceptually, we know what this code is doing. It's finding an address in memory for the appropriate enable in these target enables. Then it's finding the correct source, which is one of the bits in that range. And then it should be setting that bit to be on, which is what we're saying this line should be doing, right? Because that would enable that particular interrupt. So conceptually we understand what we're doing, but we're still struggling with understanding the actual bit manipulation code. That's the part we're still trying to understand. So let's step back for a moment and say we know that this is doing r equals 128, which is setting this bit right here. So we're saying current equals the address that we computed, and then we're setting the bit in this position. Now, if we simplify for a little bit and say that if we didn't have the source shifted right by 3-bit, then it would be the exact same thing as the target, like it would be the start of the target enables for that particular thread ID. And so that gives you 128 bits. And in that range, so first of all, it's a pointer to uint8t. So that means for pointer arithmetic, we're talking about bytes here. So then, if we're talking about bytes, and we're saying current equals current r equals this value here, so Mibble, you're saying you think it's moving the current pointer to one of the target 1 enables. So it would move you to the 3rd enable. And that's correct. Like if it was target 0, it would move you to 2002. And if it's the 2081, it would move you to the 2082, like you're saying right here, right? And that is the 3rd enable in that that array of bits. But the thing I'm confused about is starting from there, oh, I think I understand it now. So if let's draw out some memory here. So let's say I'm gonna do the 0x0c00200. So 0x 0c00, and then it's 2000. So this is target enable 0, and there's 128 bits starting from this address. So we're going to draw some bits, and we're just going to say they're all set to 0 because after you do the init, it clears them to 0. So here's 4. Here's another 4. Right, and there's 128 of these, but we only care about the first 7 bytes. So here's 2 bytes that I've drawn right here. And what we're saying is if we move over by 2, then it's gonna start you right here. So this is the place where we're starting at, and then we're grabbing a byte of that because it's if you look at the code, current is defined as uint8t. So we're grabbing a byte from this point right here. So that would be from here to right here. Right, and then within this space here, we're doing one zero 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 0000, right? That's the 128. And so now we're saying we're going to R equals those. So that sets this bit right here, which is the bit we care about. So if I'm understanding this correctly, that makes sense, what we're doing. One thing to note is I'm pretty sure setting up the pointer like this, I think that would be considered an unaligned memory access, which on like a modern processor is a bad thing. But I wonder, maybe it doesn't matter for the RISC-V chip that we have, that it's an unaligned access. Or correct me if I'm wrong, if that's not an unaligned access. Maybe I don't understand that term, but regardless, I think we understand how that works. So I want to do one more example with it just to make sure we fully understand. So this time we're going to say, instead of doing this 0x17 bit that we're setting, let's set a different one. And the other thing to note that's kind of weird about it is we're saying it's defined as 0x17, but then when we actually go and set the bit, it's like the third one from the target enabled 0 that gets set. So that's confusing to me as well. So if we go back to this interrupt thing, like assuming that each bit starts like corresponding to the different numbers, then the bit we just set would be the RTC CMP, which is not the bit we care about. So that confuses me as well. So let's walk through one more here. So as a LUTCO, you're saying source and 0x7 can produce values from 0 to 7 depending on value of source. So the shift may vary, it doesn't have to be exactly 7. Right. That's the thing I was wanting to explore in the next example. Like if I set the source to be 8, which is supposed to be the GPIO base, right? This one right here. So the example we just did was 0x17 and 0x7. So the thing I'm wondering about is what happens when we do a different value that would give a different result. So like, if we say source is 8, then that's the bit pattern for 8 right there. And then we're saying, so we want to do and 0x7. And if we do that, we'd get 0 would be the value in that case. And so if it's 0 and then we say we're doing 1 shifted 0 places, so that's just 1. So then in that case, we'd have like instead of this value right here, we just have 0x1 in this case. And then there's the other computation that we're doing, which is source shifted right by 3. So if you have 8 and you shift it right by 3, then that would give you 0, 0, 0, 1. So now in this case, you're doing base address plus PLIC enable offset plus the thread ID shifted left by the enable shift per target. But then we're adding the source shifted right 3, which in this, if it's the GPIO base, which is defined to be 8, that would be a shift by 1. So that would put you over here. And then it would set like this bit down here. I wonder if maybe the problem is that this is little endian. I think that might be what's making the difference. I'm not sure. So I'm still really confused about what's going on here. Right, because if we're setting this bit down here, that's like the 9th bit. Well, actually, the 9th bit would be correct for GPIO 0, right? Because the interrupt numbering starts at 0. And so interrupt number 8 would in fact correspond to the 9th bit. So what I'm saying here is if we look at the 0x0c00200 address again, right, So it's got, you know, a bunch of memory like this. And then we're saying we're computing an address that is from here one place over. So it starts right here, and we're grabbing a byte of memory. So that would be this right here, I think. So wait a minute, I drew this wrong. I drew 3 bits to start rather than 4. So let me erase this and draw that again. Okay, so it would be from here to here. I believe this is the address it's computing. And then there's this byte, and we're saying we want to set 1. And so that would be the low bit of the byte, which would be right here. Right, so then the end result would be like that. And that particular bit is the 9th one. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Right, that's the 9th bit within that block of memory, which would correspond to the GPIO 0, because the numbering starts at 0. Right. So it seems like that's computing the correct thing for GPIO 0. And the thing I'm confused about is what it's doing for 0x17. Because that should be giving you a value further down, not higher up in memory. So I wonder if we made a mistake somewhere, or if maybe that it just happened to work for this example, but the actual thing we're doing is wrong. I'm not sure. So if we look at the 17 example again, so if we shift it right, the value is 2. So we're adding 2 to the address, which would put you here in this block of memory. And then we're doing 17, our 1 shifted by 17 and 7. And 17 and 7. Oh, I think I made a mistake in the shifting, maybe. So if it's 17, 0x17 and 0x7, which as Lutko says is a value from 0 to 7. And then we're shifting 1 by that number. But we know because Miblo did the printf, we know that it's 128 for sure. And 128 is 10000000. But then if we're R equals this memory, that bit, that's setting the wrong bit. So I think it's just a coincidence that what I did worked out in the case of 8, because it clearly didn't work with 0x17. But I believe we are out of time for today. So we will have to continue our investigation into this stuff next time. So thank you everyone for tuning in today. Oh, what is current set to, Miblo? Current is set to the current pointer value. Right, so it's a byte that it's copying a byte from memory. So this address, right, we copy a byte. So whatever the value of that byte is, which if we're assuming that we are calling enable interrupt right after we do the PLIC init, it would be 0. And then we're R equals, and R equals is just how you set a bit, right? You R equals with a mask of what bits you want to set, and that'll set those bits. You do that all the time when you're like using flags in C. But where R equals so this part right here is the bit mask of what bits should be turned on. And so it's turning on 1 bit, and that particular bit is in the position defined by shifting left by this amount. And then once we've got the current value, we're updating it by setting the current pointer value with this variable. So anyway, like I was saying, we're out of time for today. So we'll have to continue with this tomorrow. Thank you everyone who tuned in today. And thank you everyone who watches on the YouTube archive at risky.tv. And you can follow me at HMN_risky to get updates about the series on Twitter. And currently we have this poll, so if you care about that, go vote on that. And I will see you next time. Stay risky, everyone.